Hi, I'm Kris, and my project is on a succinct logic representation for linear conjunctive languages. Linear conjunctive languages, also known as LCLs, are essential to program analysis problems. And as an example, you can see that we have some code right here, and we want to run taint analysis to determine whether the value in x can flow to the variable y. Here's a graphical representation of that taint analysis problem on the right. The value in the variable x can flow to y, but the string corresponding to this path from x to y is actually not part of context-free language, and instead it's part of the interdike language, which is an LCL. And in particular, LCLs can be represented as three different operational models. The problem is that the Trellis automata is pretty difficult to program directly on its own, so we have a three-step process. We first program a deterministic simple Turing machine. We then follow a procedure to translate this to a Trellis automata, and then finally we translate this Trellis automata to an LCL grammar to get a set of rules to represent our language. Now, each of these steps has an issue, and the first thing is that the DSTM is difficult to program on its own. Additionally, translating the DSTM to a Trellis automata often creates a Trellis automata with a suboptimal number of states. And finally, an LCL grammar is usually human readable and difficult to understand. As an example, you can see on the left, we have the CFL grammar for the Dyke language, which is very simple and consists of just one rule. However, the LCL grammar is much more complicated, and it's pretty difficult to understand on the right. Now, our solution is to simplify this workflow, and the first thing we've done is create a succinct human-readable logic representation for users to specify their language. We then provide a translation process to translate this logic into a Trellis automata, and we've also optimized the Trellis automata construction to consist of fewer states. We also don't need that third step with the LCL grammar because the logic representation succinctly defines our language. Now, moving on to an example of our logic representation, you can see here that we're trying to represent the Dyke language. And in particular, we have two sets, QA and QB, which represent the states that are propagated as far to the right and as far to the left as possible. We also have an accept and reject rules, which consist of first-order logic operating on pairs of adjacent states. In particular, this logic is translated using a procedure specified in a paper to the TA that you can see on the right here. Now, we've also observed that translating the LCL logic that we've created to its corresponding Trellis automata consists of as many or fewer states than existing approaches. So as you can see from this table here, in particular for DMN, which is interdike, we use n plus m fewer states than existing approaches. Now, to conclude, the problem we tried to solve is that existing LCL representations are unreadable and translate to suboptimal TAs. To solve this, we create a succinct logic representation that translates to a TA with fewer states. And the importance of this is that it's now much easier to specify LCLs for LCL reachability algorithms.